In our last lesson, we went over regular polygons in general. So we talked about regular being the operative word here. It has to do with the normal type, the one that you'd expect. So when we talk about a regular quadrilateral, for instance, we're referring to the square. It's the most specific type with congruent sides and angles. And regular polygons in general, any of those shapes, a pentagon or an octagon or even a dodecagon, the 12-sided shape, we're going to look at all of them. Now it's time to look at the areas of them, though, because they are a little bit different in nature. And you can even imagine right now, if I drew a pentagon and assume this was regular, I can't just look at base times height and assume that I fill up everything. I can't even figure out an actual height. So what we're going to look at is how we can, first of all, how we can come up with any area in general, and then how we can come up with a general formula for any of them based on what we're given. Okay, and it's going to start with figuring out other stuff prior to that. We have to use some trigonometry again, going back to sine, cosine, tangent every so often, but also special triangles, 45, 45, 90, and 30, 60, 90. Okay, so I'll give a little revisit of it. You're going to practice it, but it's going to be on you from there on out. Okay, these things we should know. Formula for the area of a triangle is 1/2 base times height, where you're given a base and you must create a height. Make sure that it's perpendicular to the base, and it goes from base to tip to the very edge. Area of a quadrilateral in general would be considered base times height if you could work with that. That's normally with parallelogram, rectangle, etc. Ones where, again, you have a base and you can get a height out of it, and then it goes up to another base of some sort. But we'll work with that. Okay, find the area of an equilateral triangle with side length b. I'll go ahead and draw one for you to start. Let's assume that's equilateral. Okay, and side length is b, so if it's equilateral, all of them are actually b, but I'll use the bottom one and pretend like that's your base. That's actually pretty helpful if we do that. Now remember, the area of a triangle is base times height. So it's important to figure out what the height is. Now I could draw this here, and I could call it h. That's fine, but I want to actually figure out what that is. And because this is a general one, I want to do this in terms of b if I possibly can. So this isn't exactly the best one to look at right now for everything, but check this out. In an equilateral triangle, the angles are 60 degrees each. Okay, so let me thin out this pen a little bit. This is 60, as is this, as would be this. Now I drew an altitude straight down, and in an equilateral or an isosceles triangle for that matter, this altitude becomes a perpendicular bisector for this line segment here. So actually these two parts become congruent to one another. If that matters, we'll see if and when it does. And this altitude also bisects these angles into two congruent parts. So we're going to work with those a whole lot. So these two angles now are actually congruent. If they're congruent, and this was originally 60 degrees, then these must have divided 60 in half, which means each of these are 30. Okay. I won't spend time going over that again, in the sense that you can rewind this and hear it again, but see if that can make sense to you. Even if it didn't make sense to you, check this out. If this is a triangle, okay, notice what I'm outlining. If this is a triangle, and we said this was 90 and this was 60, well, this is whatever's left that should add up to 180. This is 90 plus 60, which is 150. 180 minus 150 is 30, so this has to be 30 anyway. So see if that would make sense to you when you do it that way. Okay, I'm going to start using different colors because that's going to start throwing you off. So these were also B. So check this out here. What is the height? What is the height? Well, the height would be using some sort of trigonometry. I can either look at this side length, which is what, by the way? If the whole thing was b and this is half of it, this must be b over 2. Okay? This is half of b. This is full b. Now, if you've ever dealt with 30, 60, 90 triangles in the past, you would actually know this relationship. It goes, if this was x, this is 30, this is x, this is 2x, and this is x times the square root of 3. So we're going to have to deal with these special triangles here. This is 60, by the way. So the one opposite of 60 is x times the square root of 3, and this is 2x, etc. So this right here, and I know it's going a little bit difficultly. Maybe I should have started with a square, which will be uber simple. But this will be b over 2 times the square root of 3. Okay. Maybe I should have made the side length b to help us out, or 2b to help us out, because this would have not been b over 2, it would have just been b. But let's see if that makes sense to you. This is 30, 60, 90. If this is some length, this will be root 3 times that length. The square root of 3 is some weird number. I don't want to go into it. And this will be twice that, and that makes sense. Okay. So the area of this triangle, by the way, is 1/2 base times height. Okay. B times b is b squared. So on top I have b squared times the square root of 3. On the bottom I have 4. Now, that's not like a formula to remember. You could. That's fine. But that's just understanding the concept in the algebra of it. Instead of just saying 1/2 base times height, here we actually figured out how to get to that. And this was just in a general sense. I could have used numbers, but because I want to look at things generally for now, I want to see if you can apply that. So if, for instance, the side length was 6, then your area would have been 6 squared, which is 36, times the square root of 3 over 4. And if we're doing this in terms of units, these would be square units, because this was an area. If this was 6. 6 kind of looks like a B. Okay, so don't want to spend a lot of time doing 30, 60, 90s and 45, 45, 90s, but you kind of get the gist of that. Okay, find the area of a square with side length B. This should not, I should have done this one first. They're all B, obviously, because they're all side length. Area is base times height, so it's B squared. And that was it for the square. But I'm going to look at this in different ways, though. We're about to do that. Is there another way? Let's rewind. Okay. All regular polygons have congruent sides and angles. I'll just write them here. Sides and angles. Okay? Now we know that. Regular polygons. So they must have a... Now check this out. Here's what we're going to talk about here. If I have all congruent sides and angles in these, just like a circle, how it's kind of like everything can meet at a center point, okay? Like that's kind of what I'm getting at. If these are all congruent, they all kind of have like a middle, all right? There's a center point in this square, and there's a center point in this triangle, okay? Because they are regular. And what I mean by this is that this dot can go from here to a vertex the same distance away as it can go from here to this vertex and here to this vertex. And actually, it can even go perpendicularly from here to the side. And we're going to talk about all these terms in a second. Same with this. This goes here from here in the same length as it goes from here to there. Okay? So they all have a center point. Okay? Draw it, then draw segments from it to your angles of your polygons above. So that's what I'm about to do. So I drew a center point here. Now I'm going to draw lines from the center to my angles, or my vertexes, I should say, like these right here. I'm going to actually delete all the other stuff inside. I'm just going to remake the triangle, if you don't mind. Okay. Here's my, let's say it's equilateral triangle. Let's say this is my center point. I'm going to start drawing segments to my vertices, and they're not perfect. Sorry about that. Same with my square. Let's do it over here. Drawing from the center to the angles, okay? Okay, let's see what I instruct next. The vertex formed in the center of the polygon, sorry, the vertexes formed in the center of the polygon are called blank. So by vertexes, I mean the angles that we've now constructed. So look at this. This is an angle. This is a new angle, and this is a new angle. Same with here. This is a new angle, this, and this. So we have formed new angles within our polygon, and they happen to be called central angles. Pretty appropriate term. That is a G. Okay, and something interesting about central angles here is that they are all congruent for them, within the triangle. So these are all the same angle, etc., etc. Their measure is also equal to the measure of a polygon's, check this out, actually the polygon's exterior angles. So I'll go ahead and kind of prove that to you, okay, in two ways. First of all, let's find out the measure of the exterior angle of a triangle. Okay, if I draw an exterior angle here, remember these exterior angles, there are 3 of them. And we have found that they add up to 360 degrees. So if there are 3 that add up to 360, how much is each? In a regular polygon, you do 360 divided by 3, which is 120. Okay, so these are all 120. Now same with these. I'm going to do this one more way. If I see this as a circle, and this won't be perfect. That's not even close to perfect. I'll do it right from the center. If I see this as a circle, kind of, okay? Let's say the circle hits all these points. Let's say this is the center of my circle. A circle is also 360 degrees. So the central angles should all add up to 360 in any other shape as well. This plus this plus this in a circle or triangle will also equal 360. So if there are 3 of them and they're all congruent, they must also be 360 over 3, which is 120. So these are all also each 120 degrees. So how much are they in a square? It'll be 360 divided by 4 because there are 4 of them, which means they're 90. So they're 90 degrees, and that makes sense because we know that the diagonals are perpendicular to one another. Not only that, but they're bisectors, perpendicular bisectors. Okay, so those are exterior angles. Okay, what kind of shapes did we form? We formed triangles. Here's a triangle. Here's a triangle. Here's a triangle. All right, but I'm going to go a little deeper than that. Just give me a second here. Here's a triangle, here's a triangle, here's a triangle, etc. So I formed all triangles, but it's a specific type. It's not equilateral. Look, if this is 120 degrees, I also said that it goes from the center to the other angles at the same length. So these guys are congruent to each other, all of them. So if I have some angle here and 2 here, I'm not going to talk about side angle side, even though the triangles are congruent. But these 2 sides are congruent. So this makes an isosceles triangle. And so does this, and so does this. Not only that, but we could have said before that these angles themselves are congruent because this thing bisects them. So these are all congruent, and they're all some number of degrees, and in an equilateral triangle, they're 30 degrees each. But we formed isosceles triangles. Okay, what can you do if you find the area of one of these shapes? And by one of these shapes, I just mean one of the small ones. Okay. Oh, by the way, these are isosceles triangles as well. So what can you do if you find the area of one of these shapes? So let's say I found the area of this triangle right here. I'll even give it a blue color. What if I found the area of this triangle? What could I do with that? Well, I just talked about how this is kind of side angle side. All of these triangles are congruent to each other. So if all 3 are the same, then they all have the same area. So if I found the area of one of them, like this guy right here, then I could multiply this by 3, and then I would get the area of the other, and then I would get the area of this plus that plus that. And the area of these 3 becomes the area of the big triangle. I hope that makes sense when I say that. So I'm actually going to talk about and prove that over here, but before I do, Well, actually, no. I'll do it right now. Let's go ahead and do that. Let's take away some of these right here. Okay. First of all, the area of this square is b squared. We already talked about that. So let's prove that using triangles. I want to find the area of a square with side length b. Okay? Finding the area of one triangle first. Let's draw an altitude here because I need to find the area of this triangle. This length, we could do this in two different ways, but this length is exactly half this length right here. Okay? Because this divides into b over 2, so this is b over 2. And by the way, this is a 45, 45, 90 triangle, if you want to talk about those yet, where in a 45, 45, 90, if this is x and x, this is x times the square root of 2. Things that we're going to have to do a lot more trigonometry again, getting back into it. But anyway, this height is b over 2. So the area of this, let's make it a green triangle, is 1/2 base times height. So it's 1/2 base b times height b over 2. So the area, 1/2 times b, or b times b over 2 is b squared. 1/2 times 1/2 is 1/4. So this is b squared over 4 for this one triangle. B squared over 4. Now, if I found the area of one of them and they're all equal, then the area of all 4 triangles together is b squared over 4 times 4. I take the area of one and multiply it by 4. Then I get that one, that one, that one, and that one. So b squared over 4 times 4, the 4's cancel out, you're left with just b squared. And does that make sense? The area of the square is b squared? Yes. So the fact of the matter is, if I use the center here to create congruent triangles all around in any regular shape, like a triangle or square or whatever, and then I add up the triangles, it appears that I'm able to find the area of the entire shape. It might seem longer for something like the square, but maybe if you're given less information, maybe you're only given the height. Okay, maybe this is a quicker way, but this will be a very appropriate way for a regular polygon. So what can you do to find the area of these shapes? What we said was, when I meant find the area of these shapes, I meant like this triangle, is add all triangles up, or multiply them by the number of, so add all triangles up slash, and this is going to be the more important one, multiply by the number of triangles. Oops. Okay? So here's what's up. Check this out. We're going to write a conjecture about how we think we can find the areas of any regular polygon. So here was a regular triangle and a regular quadrilateral, right? Equilateral triangle and square. If I did the same thing here, I find the area of this triangle. It's just a little more difficult because you saw before how we had square root, blah, 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 blah. If I found the area of this triangle, I'd multiply it by what? 1, 2, 3. And then I'd get the area of the entire triangle, which was like b squared root 3 over 4. Kind of something weird, right? But the square, when I took this triangle, to find the area of all of them, I multiply by 1, 2, 3, 4. So you notice here, the triangle, the three-sided shape, I multiply the triangles by 3. In the four-sided shape, I multiplied the triangles by 4. Okay, so imagine, if you had a pentagon, first of all, how many triangles do you think you could make? Check this out. We get a pentagon. We start from the center. We draw these things to the angles. Check out how many triangles I make. And keep in mind, these are all isosceles triangles that we made. They're all congruent. 1, 2, 3, 4, 5. So if I find the area of one triangle right in here, and I multiply it by 5, then I get the area of the entire shape. Okay? So let's go ahead and write that conjecture. Write a conjecture how we can find the area of any regular polygon. find the area of an isosceles triangle. And by that, I hope you know what I mean by, that's not isosceles. I hope you know what I mean in that we have to make them first. We have to draw them out from the center, or they might be drawn for us. But you have to start from the center and draw them out. Then multiply by the number of triangles in the shape. And it's a regular polygon, remember? Okay? So write a general formula based on your conjecture. So basically what we're going to do is find 1/2 base times height. Okay? We're going to find the area of a triangle within that. So I'm going to redraw that pentagon again. Let's say, for instance, that every side is base B. Okay? Now, the height is this guy right here. So let's find the area of 1/2 base times height first. Then we multiply by the number of sides. Let's call that n, or the number of triangles, which is the number of sides, right? 5 triangles, 5 sides. So n equals number of sides. So that looks like a pretty good general formula there. And let's see if we can then apply that to other things, to other shapes. Now let's practice and see. Try with A. What kind of shape is this? I'm going to play it like Blue's Clues. I'm going to let you say it to yourself first. So say it out loud. 1, 2, 3. You probably said octagon. Let's go a little more specifically because for these we're doing regular shapes, regular octagon. The stop sign, if you will. With side length B. So let's go ahead and mark that up. Here's a B. Okay, here's what I'm going to do. I am going to create, in this instance, I'm just going to create one triangle here, okay? And we have to figure out the height as well as we do this. So this is going to take some work and some time, okay? For now, I'll call that my height. All right, I have B here, and I want to find out what these angles are. If I need to find anything here, it is these angles, because these do have particular angle measurements. This is a regular octagon, so that means they have specific exterior angles. And remember, the exterior angles are the same exact measure as the full central angle. So these two guys are congruent. If I find one, I find the other. Better yet, I could just look at one. I don't have to look at the other. I don't have to look at exterior angles if I don't want to, but because we worked with them, exterior angles add up to 360. So if I do 360 over the number of sides, and I get 45, then I get the measure of my exterior angle, which, remember, is the same as the measure on the inside. So this is 45. If this is 45, then half of it, right here, is 22.5. Okay, half of 45. 22.5 degrees. Okay, now in an isosceles triangle, by the way, so this is 45 right here. And these two sides are congruent, so these two angles are congruent over here. So that was 45, and these must be something. If I do 45 plus an angle, plus the same angle again, that equals 180. So x plus x, 2x equals 135. I subtracted 45. And get x equals 67.5 degrees. I don't know why I went with the harder problem here to start. But these are both 67.5 degrees. So I'm going to split this out for a second and give you a triangle, a right triangle, that is 67.5 degrees, 22.5 degrees, and this side length right now is half of B. If the entire side length is B, then this is B over 2. Okay? To figure out the height, I need to start using trigonometry. So this is where you have to use the calculator again. The reason why I go to such a particular problem is so that you can practice this. Okay? Now I'm going to have to find a oh, here's a calculator. Let's see. Sorry, I have one right here. Let's see what I can do with it. Where's sine, cosine, tangent on here? Here's a trig button. Okay, I found. Okay, here's what I'm going to do. I'm going to try and find this h. Let's call it h right now. Let's use the tangent function. Let's say the tangent of 67.5 degrees is h over b over 2. Okay, I'll just keep that in the denominator. I'm going to multiply this over. So h, keep writing b's for h, equals b over 2 times the tangent of 67.5. I'm sorry, my mic keeps cutting out. The tangent of 67.5 degrees. So let's see, tangent, and looking at this now, I should have used a better problem because I'm using b and it looks really weird. So this is about 2.414. Let's say 2.4. Let's divide that by 2. Do that. So I got 1.2. So h is about 1.2 b. Okay? We're doing this in terms of b. So if your b was 8, you'd multiply 1.2 by 8. Okay? So again, I am sorry that we're going with a lot of stuff like this, but you know what? You're going to use this stuff later in other math classes, so you might as well get used to using letters. And especially since I'm doing it online with you, you can ask questions as we go. So this is 1.2b right here. So the area of this one triangle is 1/2 base times height, which is 1.2b. So the area is whatever 1.5 times 1.2. I think that gives me 0.6 actually. Where's the delete button? 0.2 is 0.6. So the answer here is 0.6b squared. So that's the area of this one triangle. Now that's not an exact number because I rounded off the tangent of 67.5, but let's say that because that looks pretty clean. So if the area of one triangle is 0.6b squared, what's the area of the whole thing? Well, how many triangles are there? The same as the number of sides of the regular polygon. And they're all the same triangle. There's 1, 2, 3, 4, 5, 6, 7, 8 of them. So the area of the whole octagon is 0.6 times b squared times 8. 0.6 times 8 is 4.8. So that's 4.8 b squared. And again, think about it. If you had b as 2, take b squared, which is 2 squared, which is 4. 4 times 4.8 is probably about 20. It's 19.2. Okay. So that's units squared, by the way. All right, so that's the area of the entire thing. Okay, so that's the practice here. And I'm going to start going over some things here. I'm running out of time. Let's go over some basic terms here to see if we can really nail a more solid formula. It's just going to be a little bit shorter. Instead of finding the area for the triangle, let's do this in particular. Base of something is, let's call it the bottom. Like, in other words, you could rotate the shape and make it the bottom thing, just like this line. Okay? Bottom length. Like this triangle. Okay, we like to look at bases as the bottom. The height is always perpendicular to the base. Always, 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 always. So I should just write always, but always perpendicular to base to top of shape. Now in this case, I said the height was right here. So this isn't the top of this shape. It's just the top of this shape right here. I was just talking about the triangle in general. So that's why when we talk about height, I always want to talk about top of shape. So normally I'm going to say this is my height. That's why we're going to give this a different name. The thing going from the center perpendicularly to a side. We'll get to it. The perimeter of a shape is adding up the sides. Or better yet, check this out. If I take one base and add it together, base plus 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 base, that's 8 bases, right? Or better yet, it was the number of sides times my base. So if my number of sides is n, it's n times b. Okay, so the perimeter is adding up sides, or multiply base by number of sides. So that's going to be important. Perimeter is multiplying the base by the number of sides. The radius in this, remember when I drew a circle earlier? And I'm going to use a different color this time. When I draw a radius here, or I'm sorry, when I drew the circle here, a radius from a circle is from the center to any part of the circle. So in this case, your radius of a shape will be from center to an angle, like these guys. These blue lines I'm drawing right here, these are my radii of my polygon, just like they are in a circle that circumscribes the shape. So the radius is segment from center. By the way, I'm running out of time, so I won't be able to do the practice example with you. At least not, I don't know, people are going to come in class in a second. Segment from center to vertex of regular polygon. I'll just put polygon. Well, that didn't seem to work. Polygon. And finally, there's this term called apothem. Okay? And it's not apothem, by the way. It is apothem. So the apothem in a regular polygon is that height we were talking about, the height of the triangles that you draw. So it's the distance from center to a side drawn perpendicularly. So all of these things here, the apothe, and I assume that's plural, that might be wrong. All these are called apothems, we'll say that. Each of these, this is an apothem, apothem, apothem. Up in the, let's go back. The square, this is the apothem. In the triangle, this is the apothem. Okay? So the apothem, distance from center to side of polygon. And it's perpendicular, by the way. All of them will be in a regular polygon. And when I say distance, I mean the shortest distance. And the shortest distance is always perpendicular to it. That's why I'm saying that. They are the same. What is the relationship between the base of each shape, like this base of the triangle, okay, and the polygon's perimeter? So we already talked about this. The base of one triangle is one portion of the perimeter, and I multiply this by the number of sides to get the perimeter. So I'll say perimeter first. Perimeter is n times the length of the base. You guys are about to come in. By n, I mean n is the number of sides. I take the base, multiply by the number of sides, I get the perimeter. So area of a regular polygon. Remember before we said the area of one is if we looked at a triangle and we say it's 1/2 base times height of one of the small triangles, then multiply by the number of sides. Now that we're talking about the polygon in general, let's not say height anymore. Let's use apothem, okay? Because I want to talk about the apothem of the polygon, like this guy right here. Not the height of it, but the small part. So instead of h, we're going to be using a. Instead of b and n, what about b times n? Base times the number of sides, base times 1, 2, 3, 4, 5, is the perimeter of it. So instead of b and n, let's use perimeter, p. So now our area is 1/2 apothem times perimeter. 1/2 of this times this. Okay? So the area of the polygon, of a regular polygon, is 1/2 a times p, where a equals the apothem and p is the perimeter. So I'm not going to be able to do the practice example, but I'll get you started super quick. This is a regular hexagon. Okay, regular hexagon has central angles of 60 degrees each. Because there are 6 of them, and I do 360 divided by 6, that's 60. So all of these are 60, and because it's an isosceles triangle, These must add up to 180, so these also must be 60. So these are actually equilateral. So I have to find the perimeter, 10 times 6, which is 60. And the apothem is going to be used by drawing something from here to here. So now you have a 30, 60, 90 triangle. And if this whole length is 10, half of it here is 5. So you're going to start using all of that information to help you out. Okay? I'm going to close with that though. But perimeter, or area, of the polygon is 1. I might cut off at the very end. Perimeter is 1/2 apothem times perimeter. Okay? Good luck.